In this section, we'll discuss polar coordinates. Throughout most of your physics career, you've probably used Cartesian coordinates, x hat, y hat. And so these are basis vectors, one of which points in one direction, the other of which points 90 degrees away from that. So they're orthogonal. But they're not the only set of basis vectors in which we can work physics problems. Another set that you will frequently encounter is two-dimensional polar coordinates. And in this basis, we have two different basis vectors. For two-dimensional polar coordinates, instead of using x hat, y hat, we take a vector which points from the origin, which we have to pick no matter which basis we use. We have to choose an origin. And we take a vector and point from the origin to the point of interest. So this is a vector pointing from the origin to the place that we're interested in tracking. This vector having unit length, this vector pointing from the origin to the point in question is the radius vector r hat. Now at that point we can define two new basis vectors, both of which have a length equal to 1. So that's one of the most important features of a orthogonal set of basis vectors, is that they have a length equal to 1. So at this point r, we define this new basis set of vectors. One vector is going to point outward along r vector. This is going to be r hat, so that runs parallel to r. So these two vectors run parallel to one another. And because we're thinking of motion in two dimensions here, we need a second basis vector, and we're going to use a second basis vector which points 90 degrees away from this r hat. It's going to point like this. And that vector we're going to call phi hat. Phi hat points in the direction of increasing angle phi. So if we measure our angle phi relative to the x-axis, our angle phi looks like this. And so the direction of increasing phi is counterclockwise, and that direction is expressed by phi hat. So again, in the two-dimensional polar coordinate system, our basis vectors are not x hat, y hat, they are r hat and phi hat. Now one advantage of using x hat, y hat in dynamical problems is that they don't change. Once you've assigned an x direction and a y direction, you can have your physical object moving about in space however it likes, and x hat and y hat always remain exactly the same. They point in the same direction. In other words, the time derivatives of these basis vectors x hat, y hat is 0. But if we choose this new basis set, r hat and phi hat, you can see that depending on where in the xy plane we are, those basis vectors are going to change. So let's look at what that looks like. So consider a point out here defined by the vector r at time t1. There may be some object, some point mass that rests at position r at time t1, and then at some later time it might move to this position over here. And in that case we have another radius vector, another location vector, which we might call r of t2, so at time 2. When our object is at position r at t1, the r hat basis vector points like this. Remember, it always points parallel to the r vector. R hat points like that, phi hat will point like that at a right angle. But at some later time, t2, our position vector r has changed, and therefore our r hat and phi hat have to change. Now, at this new position, r hat points outward like this, and phi hat still points at a right angle, so it points like this. And so this is an important difference between the x hat, y hat, and the r hat, phi hat coordinate systems. R hat and phi hat will actually change with time. They'll change as the object is moving around. Whereas x hat, y hat, they stay fixed. They never change even as the object moves around. Now this introduces some additional complications when we want to think about the dynamics of our system in the polar coordinates. It simplifies certain aspects of problems, but it can complicate others. If, for example, we have a force vector which acts radially, so there's a force acting on our mass which always points toward the origin, say, that force vector will always run parallel to the r hat vector. And so in a case like that, it might make a lot of sense to use r hat, phi hat as our basis vectors. But as we see here in this example, the time derivatives of these basis vectors are non-zero. So next, let's think about how to calculate the time derivatives of these basis vectors so that we can do the dynamics properly in this coordinate system. So to motivate this discussion, to motivate why we need to actually calculate the time derivatives of our basis vectors r hat and phi hat, let's recall Newton's law that F equals ma vector. Now remember that the acceleration vector a is the second time derivative of the position vector. So in other words, in order to apply Newton's laws, we need to be able to calculate the second time derivative of the position vector. Now, when we write the position vector in x and y hat, calculating its time derivative is relatively easy. So if that is our position vector, x times x hat, y times y hat, then the second time derivative, well, that's easy to calculate. That's just going to be x double dot times x hat plus y double dot times y hat. But what if our basis vectors themselves have non-zero time derivatives? In other words, what if we write our position vector using r hat and phi hat? Then we have to apply the time derivative twice to r as a scalar times r hat. And this is going to be more complicated. So let's look at what that looks like first. Okay, so our position vector looks like this, of course. It's the scalar r, so the magnitude of the r vector, times r hat, the direction of the r vector. Okay, taking a first time derivative, that would represent the velocity of our object in motion. And so we need to apply this time derivative to the product of scalar r and r hat. If you recall your product rule, you will get this, r dot r hat plus r times r hat dot. Now, this term here just represents the rate at which our moving object is moving outward away from the origin. So this is just the radial velocity. This term here, however, represents the rate at which the basis vector itself, r hat, is changing as the object moves around. When we use the x hat and y hat basis vector set, we don't have to worry about this derivative. But when we use the polar coordinates, we do. Okay, so we'll come back to that. The next thing we need to do is to calculate a second time derivative of our position vector, because remember, we're interested in the acceleration. So that's going to be the same as applying another time derivative, d by dt, to r dot r hat plus r times r hat dot. Oops, start that again. R hat dot. Okay. We can again apply the product rule, and what we get is this. We can see we get two time derivatives of the r from here. Then we apply this time derivative to this term here, we get this guy. We apply this time derivative over here, we get that, and then to that, we get this. And so what we get for this acceleration vector in the polar coordinate system is r double dot r hat. Okay, so that's the acceleration along the radial direction, that's one term anyway, plus 2 r dot r hat dot plus r times r hat double dot. And it's these terms that are different for the polar coordinate system. So now we need to calculate the time derivative of the radial basis vector r hat, and then the second time derivative of the radial basis vector. So let's look at how we do that. Okay, so this is what that looks like. Say at time t, our position vector r points here. So there's our position at time t, and at some later time, a little bit later, delta t, our position vector now points here. So here's our new position, and here's our new position vector. At time t, r hat looks like this. See r hat at t. At time t plus delta t, r hat looks like this. And so what we're interested in calculating is how does r hat change over time. So we're going to calculate this difference. R hat at time t plus delta t minus r hat at t. So highlighting just the basis vectors now, r hat at t plus delta t. We stick their tails together like this at the origin. And what we have here is a triangle where each of the legs of the triangle has a unit length. So remember that these vectors are by definition unit vectors. They have length equal to 1. The length is equal for each of these vectors. And the difference between these two vectors is the change in the vectors. And so the change in the vectors can be represented as another vector itself here, delta r hat. So our trick is to figure out how to write delta r hat in terms of either r hat of t or r hat of t plus delta t. We'll use r hat of t. So how do we write delta r hat in terms of r hat of t and the other basis vector that we have, remember, phi hat of t? Well, one trick we can use is the fact that r hat of t and r hat of t plus delta t, they have exactly the same length. So in other words, as the object moves from r of t to r of t plus delta t, r hat can't change length. And so if delta r hat had a component along r hat itself, in other words, if there were a component of delta r hat that ran along r hat, that would mean that r hat would change magnitude over time. Change. Okay. So if delta r hat had any component along r hat itself, then as time marched along, the basis vector r hat, its magnitude would actually change. So the vector would lengthen or shorten depending on which direction delta r hat pointed. We can't have that. By definition, we can't have that because r hat, no matter what time it is, can't change length. Therefore, we require that however we can write delta r hat can have no components along r hat itself. So the two vectors must be totally orthogonal. Well, the only orthogonal basis vector we have for r hat is phi hat. Therefore, delta r hat must run parallel to phi hat. So we have this requirement that delta r hat must run parallel to phi hat. You might be able to convince yourself that as the object of interest moves from this point to this point, phi, the angle, is changing. And so you can show that this angle between r hat at t and r hat at t plus delta t, that this angle here is delta phi. So whatever the change in the angle is from one time to the next, we know that if delta t is small, that this delta phi angle must be phi dot, so the time derivative of the angle phi as the object moves around in space, times the small time delta t. And we're not showing it rigorously here. The book does a little bit better job of doing that. But the basic idea is now we have an expression for delta r hat. It has to be very nearly delta phi times phi hat. And that is, as we've just said, phi dot, so we can write that legibly, phi dot times delta t times phi hat. And so in other words, if we divide through by delta t, what we find is delta r hat over delta t is equal to phi dot times phi hat. And so that's the time derivative that we were looking for earlier in our expression when we were trying to calculate the acceleration. And if you remember, when we were writing our velocity vector, the time derivative of our vector, that is r dot times r hat plus r times r hat dot. Well, we just worked out r hat dot, and so now we have for our velocity vector r dot r hat plus r phi dot phi hat. So our velocity vector has two components. One of the components points along the radial direction. That makes sense. That's just the radial velocity. Then the other component points orthogonal to the radial velocity. This is going to be the tangential velocity, the angular velocity. Now, to calculate the acceleration, of course, we need to apply yet another time derivative to this expression. So we got this, and this, and this, and this. And so you can see that when you apply this time derivative, you're going to have to apply it to this term here, to this term here, then you're going to get three terms here due to product rule. One of these terms here is going to actually involve phi hat dot. The book works through all of this. I won't belabor the point, but the point is that what you'll end up getting for your acceleration vector written in polar coordinates is a little more complicated than what you get in Cartesian coordinates. You'll get two terms that point along the radius direction, the radial direction, which is, there's one of the terms. So you have, here is the acceleration having to do with changes in the radial distance from the origin. And then you get this other term, which, as we'll see, has to do with centrifugal accelerations. Then you get another component for the acceleration vector, r phi double dot. So this is the angular acceleration here, plus another term that kind of mixes the velocities. And all of these guys point along the phi hat direction. And so the acceleration as written in polar coordinates has an r hat direction, an r hat component and a phi hat component. Keep in mind now that each of these terms has two time derivatives for one of the coordinates, and then another term having to do with other effects in the polar coordinate system. So as I said already, this term here has to do with centrifugal accelerations. This term is just your regular angular acceleration, and then there's a term here which turns out to be related to the Coriolis acceleration. And we'll come back to all this later in the semester. Okay, so great. How do we use this information? How do we apply this relationship now for the acceleration vector? Well, let's look at the example given in the book here. Let's imagine we have a skateboard and a half pipe here. So here's our little half pipe. Here's the center of the half pipe, say. We imagine that the half pipe is a hemisphere, so it's exactly circular for the region that we can skateboard along. Here's our skateboard, which looks awful in the sketch. So to locate our skateboard, we have a radius vector. We'll have it point from the center of the half pipe to the middle of the skateboard. So that's R. Now our skateboard, as it rolls back and forth along the half pipe, experiences two different forces. One force is obvious. It must experience a weight downward. The other force is maybe not so obvious. It must experience a normal force perpendicular to the surface of the half pipe. If there weren't a normal force, the skateboard would actually just fly right through the half pipe. And in fact, if the half pipe were to break or not be able to support the weight of the skateboarder, then you would see a case where the normal force wasn't enough to keep the skateboard from falling through the half pipe. Okay, so now what we want to do is to express these two forces in terms of our polar coordinate system. So remember, we have our two forces, sum of the forces F, mg plus n. That's got to be equal to, according to Newton's laws, mr vector double dot. Okay, so let's think about how to do this problem using our new polar coordinate system. So we know our normal force always points along the radial direction. The normal force must point along the radial direction. It cannot point along the phi direction, because that means that the normal force would then point tangential to the half pipe, and then it wouldn't really be a normal force. So one thing we know for sure is that the normal force must point along the radial direction, and in fact we know that it has to point inward toward the origin. So it actually points in the opposite direction of r hat. So we'll say n, the normal force, is parallel to negative r hat. Now I don't know what the magnitude of n is going to be yet. It turns out that n can be a little complicated, but we can definitely infer that it must point along the negative radial direction. Okay. For our weight component, our weight force, let's imagine that we have our skateboard at some point r. Here's our skateboard, and the weight vector looks like this. It points downward. Our skateboard is at some position r, and we might measure the angle for that position, phi, relative to straight down. So we're going to make phi point like that. So there's phi. And what we'd like to do is to resolve our weight vector into its r and phi components. Okay, let's draw our weight just a little bit bigger here. Remember, this is the point at which our skateboard is at some instant in time. We're going to measure that angle phi. Here's what the weight vector looks like. And so what we want to do is write our weight vector using r hat and phi hat. Now you can do the trick. The book walks you through the trick, how to resolve the components. I'm going to use a slightly different way to work out what the components must be. I know that the magnitude of my weight vector has to be mg. So that product must appear somewhere in the expression for the weight. And then I've got two components, remember, for the weight. I'm going to have some component times r hat plus some other component times phi hat. And now we know, hopefully you know, from having taken some intro physics classes, that the things that appear here and here are probably going to be sines and cosines. And so the way to work out which is the sine and which is the cosine is to think about how the weight vector would point at different orientations for the skateboard. So for instance, if the skateboard were at the bottom of the half pipe down here, at that point phi is going to be exactly equal to 0 degrees. Okay? And when the skateboard is at the bottom of the half pipe, the radial vector points directly outward. We know also that the weight vector in that case must also point directly outward along r hat. So in other words, when phi is equal to 0, so we'll say when phi equals 0, the weight vector must run parallel to the radial vector r hat. And so when we're thinking about whether there needs to be a sine or a cosine here for the r hat component, we'll ask ourselves, okay, so sine or cosine, which of those two is non-zero when phi is 0? Well, it's going to be the cosine. And so the component here for the r hat part of the weight vector is going to be cosine. That leaves sine for the phi hat component, but we need to ask ourselves the question, is it a negative sign or a positive sign? Negative sign or a positive sign? Well, again, we can consider an extreme example. Let's imagine that the skateboarder makes it all the way to the top of the half pipe. So he's at 90 degrees here. And in that case, we know that the weight vector should point downward like that. Well, that's negative phi hat. So in other words, when phi is equal to 90 degrees, all of the weight points along the negative phi hat direction. And so that means that this term here for the phi hat component of the weight has to be negative sine phi. We also know, of course, that when the skateboard is at 90 degrees, r hat points outward like this, and so none of the weight component points along r hat. So when phi is equal to 90 degrees, there should be no r hat component to the weight, and indeed, cosine of 90 degrees here, you can see, is 0. And so again, our weight vector, just to write it a little more cleanly, has to be mg cos phi times r hat minus sine phi times phi hat. Now you can work this out trigonometrically. For some people that's easier to do. This sort of intuitive way of working it out is a lot easier for me. And you'll see that we'll use this approach over and over again to work out whether the sine or the cosine needs to append a different term. Okay, so there's our weight. Now let's go and work out what the normal force has to be. Okay, so to work out the expression for the normal force, let's return to our equations for relating force to accelerations. And we're going to focus here just on the radial component. So now we're thinking of the radial forces, F sub r, the net radial forces. So there's two forces along the radial direction. There's the normal force, which, remember, we know that that points along the negative r hat direction. So we're going to use capital N here to represent the magnitude of the normal force, and then we have to put a minus sign up front to make sure we get the direction correct. Then the other force in the radial direction is the radial component of the weight, so that's going to be mg cos phi, which we just worked out. And Newton's second law tells us that this all has to be equal to the radial acceleration, the component of the acceleration vector along the radial direction. So that's going to be m times r double dot minus r phi dot squared. Okay, perfect. Now, in order for our skateboarder to remain on the half pipe, we require that the radial distance from the center of the half pipe to the skateboard, that radial distance has to be a constant. In other words, that radial distance can't change. And so what that means is that r dot has to be equal to 0 and r double dot has to be equal to 0, okay? So the radial velocity has to be 0, otherwise the skateboard is falling through the half pipe, and the change in that radial velocity with respect to time has to be 0. So that means that this is 0, and we can rewrite this equation to solve for the normal force. So what we'll find is we get normal force, the magnitude, is equal to m r phi dot squared plus mg cosine phi. In other words, the normal force is the sum of the radial component of the gravitational force and this term, which represents the centrifugal force. So the normal force has to balance both of those effects, gravity and the centrifugal force. And intuitively that makes sense. The normal force provided by the half pipe better be able to balance the outward tendency, that the centrifugal force on the skateboard, and the gravitational pull on the skateboard, both of which want to pull the skateboard through the half pipe. And so we'll go ahead and stop there. The book works the rest of the problem out and shows you that the motion of this skateboarder along the half pipe actually resembles the motion of a pendulum, and so you end up getting a pendulum equation for the dynamics of the problem. And we'll run into the pendulum equation very frequently in this class, so you want to make sure to familiarize yourself with that.